Hi, I'm Shashank Verma, and today we are going to talk about fine-tuning the new GPT-OSS models from OpenAI on a domain-specific use case with NVIDIA NeMo framework. To set some context, OpenAI recently released two new open weights models, GPT-OSS 20B and 120B. They deliver strong performance on reasoning, tool use, and coding, among other tasks, and can be further customized to obtain even better accuracy on domain-specific use cases. NVIDIA NeMo framework is a scalable, end-to-end generative AI training framework for large language models, multimodal models, as well as speech AI. The NeMo framework added day zero support for accelerated fine-tuning of these models with advanced model parallelism and memory efficiency techniques. Let's take a look at a quick tutorial on how to fine-tune GPT-OSS with the NeMo framework. The NeMo framework is open source, and you can find the Jupyter Notebook tutorial in the GitHub repo. The dataset we will be using pertains to customer service, which represents a critical use case for many enterprises today. For solving this problem, organizations often deploy multi-agent systems featuring a router model and several specialized sub-agents that handle different aspects of the problem. In this tutorial, we will fine-tune the GPT-OSS 20B model to function as a router that processes user queries submitted via emails and routes them to the appropriate department for resolution. Note that while this is not a reasoning-focused dataset, you can certainly fine-tune for that as well. To get started, you will need access to at least one NVIDIA GPU with a cumulative memory of 80 GB, as well as a Docker-enabled environment with NVIDIA Container Runtime installed. In addition, get your Hugging Face access token and log into a Kaggle account. The first step is to obtain the dataset, which you will do from the Kaggle website for the dataset, which is the multilingual customer support tickets. You can go ahead and click the download button on the top right hand side and download the dataset as a zip file. Furthermore, you can follow the instructions on the README to extract the dataset. Once you've downloaded and extracted the dataset, the next step is to download the model, which you can do by cloning the Hugging Face model repo. Followed by this, the next step is to start the NeMo framework Docker container. Note that NeMo framework comes in two forms. You can either pip install the Python package, or you can also get started with the Docker container, which is the route we'll be using over here. Once you start that Docker in interactive mode, you can start Jupyter Lab inside of it and navigate to the notebook to get started. The first part of the notebook pertains to preparing the dataset. This is done by reading in the dataset and dropping any rows with missing values. Then we configure the training, validation, and test splits. After that, we transform the data by defining the task in the prompt. Note that the input in this use case are the details of the email that the customer sent to the support agent, such as the subject and the body of the email. And the output here is the queue or the department it must route that ticket to. And that's how we are fine-tuning the GPT-OSS model into a router model. Finally, this code saves the dataset into a folder which will be picked up by the data loader at training time. In the next part of the notebook, we make certain configurations for fine-tuning, including configuring your Hugging Face token and optionally a weights and biases API key for experiment tracking. Next, we import the Hugging Face checkpoint and convert it into a NeMo 2 compatible format. We do this by using the llm.import checkpoint API. And of course, we specify the path to the model repo that we cloned earlier. Note that here we wrap this llm.import checkpoint API with the NeMo run.partial primitive. Now, NeMo run is a subcomponent of NeMo framework. It allows you to define and configure complex experiments with multiple tasks all at once from potentially the comfort of your Jupyter notebook for deferred execution. In short, you can configure your task or function that you want to run. Then you can set up executors for different environments, such as local executor, a Docker executor, a Slurm executor for a Slurm environment, or even a cloud environment. And then you can execute your configured task on that environment with the run.run API. For this demonstration, we do execute it locally over here using the local executor. And then, doing this will run the conversion process. And throughout this notebook, we follow this pattern of configuration first and execution later. After the checkpoint is converted, we can instantiate the recipe for fine-tuning. NeMo framework provides expert-built recipes for training and fine-tuning several popular models such as GPT-OSS, and you can instantiate these recipes and configure portions of it for your use case, such as configuring your data loader to specify the prepared data directory. Then also configuring the logger to specify where the checkpoints will be saved, as well as the weights and biases project name and the run name in case you're using that for experiment tracking. You can also make other configurations such as the auto resume policy, as well as trainer configurations such as the number of training steps and the learning rate. Finally, NeMo Run provides a way to visualize this recipe in the form of this tree of some modules and the different settings. You can use this for a quick review before you execute the fine-tuning run, which you can do by using the NeMo Run.Run API and provide the path to the recipe object as well as the executor, in this case a local executor. The contents of the output cell can be used to track the progress of the training run. In this case, I have the run already executed and my logs are saved at this specified location. Next, for a quick sanity check, we run generation on the test set to see how the model is performing. We identify the path to the checkpoint that we just trained, and then we use the llm.generate API to run generation on the test dataset. And note that here we pass in the same data loader that we used during training. It automatically picks up the test split to run the generations. Then we again run it using the run.run primitive from NeMo Run. And after it gets executed, it saves the result into an output file that you can specify beforehand. And when you take a look at the results, you'll see it in this format where the input pertains to the query that was sent to the model. The label is the ground truth from the test set, and then the prediction is what the model predicted the answer to be. Now, of course, you can use these predictions to run any eval metric calculation, such as in this case, we run F1 scoring, and then you can choose to train for longer to iterate on and refine the model to improve these scores. And finally, the last bit is to export the model to the Hugging Face format, which can be picked up by an inference deployment solution such as vLLM or NVIDIA NeMo. Before we do the export though, we can merge the LoRa adapter that was created with the base model to create a unified weights checkpoint. And then finally, you can use the llm.export checkpoint API to create a Hugging Face format .safe tensors model. Note that NeMo framework also supports exporting a TRT LLM engine for optimized inference deployment, and you may find detailed instructions around those in the NeMo framework documentation. Congrats! At this point, the model is ready for deployment. Thank you for watching.